All right. Good afternoon, everybody, and welcome to the PetroTeach webinar on capillarity in porous media. My name is Hassan Karimai, represent PetroTeach today and act as moderator in this webinar. As you already heard from the organizer, you are entering as listening only mode and muted. Before we proceed the event, let us check if you received the voice properly. There is a window in front of your platform, and by clicking on the arrow, you will see the full window version with a chat box. Please type the word hi or hello or something so that we make sure we have established the full communication. Yes, great. Seems everything is okay. Okay, the outline of the two-day webinar begins with a brief introduction to PetroTeach. And then we introduce our distinguished instructor, Professor Hassanizadeh. Next, we follow and listen to the webinar lecture, which lasts 45 to 60 minutes. And finally, we will have Q&A session for approximately 10 to 15 minutes. So PetroTeach is a global provider of high-quality training solutions to the oil and gas industry, and currently we are providing about 150 training courses by up to 50 distinguished instructors with high track record from academia and industry. Our training styles include online, public, and in-house courses. Due to the COVID-19 pandemic, PetroTeach is mainly focused on the distance learning. For more information, please visit our website and also download the course catalog for 2021. You may also follow us in social media like LinkedIn, Instagram, and Facebook. And also, please do not forget to subscribe our YouTube channel to watch the related videos and receive future videos. So the event today is part of the 20 webinar series that PetroTeach is offering during this year. For September, we started with Nightmare of Gas Hydrate Blockage by Professor Bahman Tauhidi, followed by Advanced Petrophysics by Mustafa Haqqaq. And then Dr. Andrew Rose gave a webinar on seismic reservoir characterization, and also Jerry Rusnak on hydraulic fracturing. Dr. Feranek Hasyuk and Dr. Sergey Ishutov talked about 3D printing, and the last webinar in September was given by Professor Wumi Iledar about petroleum economy. Then in October, we started by casing and cementing by Jerry Rusnak, followed by Professor Reza Azin, who talked about classic measurement versus image processing, and then Professor Maria Muti talked about advanced analysis of carbonate system, and finally, Dr. Mazda Irani, who talked about SAGD and solvent SAGD design and analysis. And also in November, we started by borehole image application by Imane Ferhat, followed by Professor Shahab Muhaqqaq, who talked about application of artificial intelligence and machine learning in petroleum engineering. And then David Garner talked about geomodeling, Fayez Makkar on well integrity management system. And also last week, we had interesting talk about plug and abandonment of the wells by Dr. Mahmoud Khalife. And today we are pleased that Professor Hassanizadeh will talk about capillarity in porous media. And also in December, tomorrow, we will have Professor Izzat Haydari, who will talk about fundamentals of carbonate reservoirs. Next week, David Garner will talk about the role of geomodeling in the multidisciplinary team. And also Dr. Babak Jafarizadeh will talk about petroleum investment analysis. And the last talk in December or in 2021 will be given by Dr. Feranek Hasyuk on carbon capture, utilization, and storage. So we welcome and are pleased that Professor Hassanizadeh can join us today. The topic of his presentation, as you can see, is capillarity in porous media. Today we will receive latest updates and important considerations on this subject, which is related to the Professor Hassanizadeh valuable experiences and comprehensive research on the topic. As you can see, Professor Hassanizadeh has more than 40 years experience in theoretical, experimental, and computational studies of flow and transport in porous media. He has worked at RIVM Institute, Delft University of Technology, and Utrecht University, where he is currently Emeritus Professor of Hydrogeology. He has more than 300 publications on theories of flow and transport in porous media, pore network modeling, and experimental studies of two-phase flow, including studies of low salinity effect. He has been editor of major journals such as Advances in Water Resources, Water Resource Research, and also Transport in Porous Media. He is co-founder and managing director of International Society for Porous Media, or Interpore. He is elected Fellow of American Geophysical Union in 2002 and American Association for Advancement of Science in 2007. And also he's selected as 2012 Darcy Lecturer by the US National Groundwater Association and received the Royal Medal of Honor Knight in the Order of the Netherlands Lion in 2015 and Robert Horton Medal of American Geophysical Union in 2019. So let's move to the presentation. I want to remind you all that you can post your questions using the same chat box introduced at the beginning, and at the Q&A, we try to answer the questions. So I'm going to hand over the talk to Professor Hassanizadeh to address his presentation. Yes. Here you are, Professor.
Okay, can
Yes.
you see my screen?
Yes.
Okay,
Definitely.
wonderful. Great. Well, hi everyone. Thank you for joining. Too bad we cannot see each other. I have the habit of, when lecturing, to interact with the participants and audience and ask them questions and get responses back. So no, unfortunately, we cannot do that. Hopefully in near future. So I'll talk about basics concepts of capillarity. In fact, many of you may know some of these stuff. So yeah, forgive me if some of the things are too familiar for you, but hopefully there are also points that would be new to you or would be something to consider later on. So I'll have an overview. I must say, this is a very, very, very short version of the short course that I give on this subject as part of the Petro-Teach short courses. So I will just go over some aspects, and now hopefully at some other point the details will be given in the short course. So I'll look at capillarity, its underlying concepts, and then capillarity at the porous scale under static and dynamic conditions. At macro scale, what are the basic concepts, and so what are the advanced theories, and if there is time, some computational and experimental studies we have done, I'll share with you. Now, see, the capillarity comes from the fact that you have two immiscible phases, and these two immiscible phases have an interface between them. So the first question actually is, what is an interface? How is it defined? What are its properties? What are its characteristics? And why is that then? How does capillarity come in when you have an interface between two phases? Now, so that's a whole long story. I'm not going to get into that. As I said, this will be in the short course. So one of the major issues is the surface tension that exists in an interface. And the question is, okay, what is the surface tension in terms of molecular interaction? You know, everything that we have relates to the interaction among molecules. And that's the starting point for everything. If you think of what is viscosity, what is the diffusion concept, and the same surface tension has its roots in the molecular interaction. And if you look at what is explained in literature about what is surface tension and its molecular interaction, and hopefully this links works. Let's see. Yeah. You see that there are concepts given that are actually not quite right, because almost everywhere in the literature, let me bring in like this example. Some of these are from academic sites, universities. For example, this tells you, oops, I cannot use my pen here, unfortunately. But if you look in the middle of the page, this one here, I make it larger. Let me move this away. You see, it shows the molecules have attraction among them at the surface, and it says that this attraction at the surface is not balanced in the perpendicular direction to the surface, and inside the fluid they are balanced, and those are, say, the molecule in the middle shows that all forces in all directions. But these are all oh, it's actually here also, you can see it. These are all attractive forces. If you were going to have this molecular picture, that means within the fluid we will have only attraction, and that's wrong. We know that within a fluid we have pressure, which is compressive force. So where are the compressive forces here actually? And that is not properly shown here. And you can just go on and look at the literature. Wikipedia has it wrong. I had Wikipedia here, but well, anyway, you can look, even MIT has it wrong, that they all show pictures like this, where they show an imbalance of forces at the surface. They say, okay, that's why you have surface tension, because there are attractive forces that are imbalanced. But inside the fluid, it also shows attraction forces, which is not correct. So the question is, what is the correct description of? And here are some more from Wikipedia and so forth. And I'm going to explain that, what the correct molecular description of source of interfacial tension is. You know, actually, molecules in a fluid, they have two sorts of interactions. Let me get my pen back here. So one is indeed interaction between molecules, as was shown attraction between molecules, as was shown in those images I just showed you. But the other thing is that the molecules hit each other. They are moving at very, very high speed. They hit each other. They hit each other back and forth. So they have attraction forces among them, but they also exchange momentum, and they do that by hitting each other. And exchanging momentum, as you know, the change in momentum per unit time, that is force. So, but look at these two forces. The forces between two molecules is a function of the distance. So the attraction forces are a function of distance between the two molecules. Here at the horizontal axis, the distance is shown in angstrom. And of course, if the molecules are too close to each other, that is this range here, they'll be repulsing. But when they are beyond that, they will be attracting each other. Except that this attraction force is a maximum at a very optimum distance, and then it quickly dies off. And in liquids, the graph that is shown here, this is from the paper that is shown down here. In the liquids, there is a maximum that force is actually quite considerable, but only at an optimum distance between them. And farther away, the force is zero. And if vapors, because the molecules are very far from each other, that force is almost zero. So there is attraction forces. And then under normal conditions, let me see whether I can get rid of these drawings. No, that's okay. In normal conditions, I hope you can see the arrow here. That is this arrow here. The distance between molecules of fluid are such that these attraction forces are almost zero. Okay, So this is the attraction between molecules. But as I said, in addition to that, we have momentum transfer, and they hit each other, and that is the source of pressure. The reason that we have the pressure inside a fluid is because these molecules hit each other. If you can imagine an imaginary surface, if you have a bucket and then you have molecules moving around in this bucket, and the pressure that the piston feels is the force of molecules hitting it and then going back, hitting it and going back continuously at enormous speed and in a very, very large number of collisions per unit time. And that is the pressure that is, and in fact, you can, I'm not going to go into details, you can show here that the momentum exchange is the mass times the velocity. The velocity Vx, when it hits the piston, becomes 0, and then it goes the other direction. So we have 2 times Vx is the velocity change times the mass, that's the momentum. If you sum all of this over the molecules that hit this piston, we get pressure. And that is from one molecule, and is sum over all the molecules. Then you can see that the pressure is actually the mass density times the average of kinetic energy of the molecules. That's what pressure is. Inside the fluid, this is very large. Attractive forces between molecules are very small, and therefore we have pressure inside the fluid. Those are the attractive. When we go to the interface, at the interface, the molecules get separated from each other. You see, inside the fluid, the molecules are much closer to each other. Near the interface, as they are in connection with air, for example, or its own vapor, then the distance between them is much larger. So now if you go back to the drawing I showed you, that's here, you see that now the molecular distances approach this this distance between them, and you have a large attraction force. And also because the molecules are much fewer, farther apart from each other, the momentum exchange becomes smaller. So at the interface, 2 things happen. The momentum transfer between them becomes smaller, so that's the source of the pressure part. The collision part, that's smaller, and the interaction becomes bigger, and that gives you surface tension. That's why inside the, and this is especially in this direction, because in the normal direction, you still have the compression forces and the you have fluid which has very little attraction towards to the air molecules. So the attraction is mainly transversal to the or in the plane of the interface. So that is why you have surface tension, and this is not really properly explained in the literature. So I thought you will share with that. So, and I'm not going to. Oops. Let me move this. Okay. Now, surface tension is actually interfacial energy. It's energy per unit area of the interface. And to highlight that, I'm going to show you this. Let's see. I need my mouse. How do I get my mouse? Hold on a second. Oh. I want to play this movie, but somehow I have lost. Oh, here it is. Okay. There. What you see here is a thread. I'll go back. See a thread, and then it was put in soap water. So you see that is a thin layer of soap that has been formed between that thread and the frame around it. And by pulling on that thread, you see it extends the interface, but it goes back. So that's energy per unit area, as I mentioned. Let's look at that again. So because you know things in the world do happen spontaneously only if energy is released. By pulling this on this thread, we store energy there. So we are adding energy by pulling it. And then when you leave it, the energy is released. So that's energy per unit area, and that's a measure of the surface tension. There is another video I like to show that shows surface tension. You can also see it as force per unit length. So let's hopefully that can be shown here. It's coming. And this is also a frame that is put inside soap water. And yeah, it's coming. There you go. No, that's the frame. And then soap water is added. And then a small rod is put on that frame, put in the soapy solution. And if you take it out, there is a thin film formed around that rod on that frame. And then when it breaks, so let's do that again. When it breaks it on one side, the rod is pulled by that interface. So this is force per unit length of the rod that was applied to it. So I hope I have shown to you that surface tension is energy per unit area or force per unit length. Now, then comes the concept of wettability. And to show that wettability, I'd like to show you another movie. Hopefully this will work. Yeah. And it is coming. Hold on. No. Okay, so we have two glasses. One of them is empty. The other one has some liquid in there. And we want to empty one liquid into another liquid via the air. As you can see, the liquid is empty into the air, but of course is empty through that thread. And it just stays on that thread against gravity and is emptied into the other glass. And why is that? Because that thread is very hydrophilic and therefore doesn't let the water leave that thread. So why is that? What is the force that is holding that water into that thread? Now, these are all related to wettability of solids. A solid is said hydrophilic if it holds the water. And why does it hold the water? The reason is, again, in the energy. Let me get my pen. The interfacial energy of solid-air interface is much larger than the interfacial energy of solid-water interface. So that is why the solid would like to have water next to it, because it will go to a lower energy state. In fact, in the world and the physics, things happen because they go to a lower energy state. They are spontaneous only if the system goes to a lower energy state and releases energy. And that is behind the concept of wettability. The whole system goes to a lower energy state. And you saw that here. But actually, I'm going to show you to you in a much better way. Of course, the reverse is that we have a hydrophobic solid, which doesn't like water. In that case, the solid air interfacial energy is less than the solid water interfacial energy. Now, to show that this is all related really to this energy concept, I'm going to show you this experiment that oh, okay, so maybe before that, I also explain this, or pose the question, so why does, for example, water spread over a hydrophilic surface? And you know, you saw the thread, but of course, you know that if you put a droplet on a hydrophilic surface, what happens to this, right? We'll go back to this. Now, why all of this is happening, I'm going to share with you this experiment we did a few years ago. in the lab. And the experiment is as follows. We have a lab space where everywhere the temperature is the same. So we have thermometers all over inside this bath of water in the air. And then we have a bucket, a bath of water. And we have here a piece of a plexiglass plate, shown also here, a perspex, and we stick a piece of paper on this plexiglass plate. I think I have a photo of that here. Now, this is the plexiglass plate with 4 pieces of paper that are pasted on it. Okay, and then we fix this in space, and then we raise this bucket of water until water touches the bottom of the paper. So the paper is seen, this thin white piece is that is pasted on the plexiglass. And then we're going to, I'm sure you all know what happens. This is a hydrophilic paper. So as soon as water touches the bottom of that paper, water rises up in that paper. Now, that is by itself amazing, isn't it? Water goes up against gravity. Water moving inside the pores of paper is against viscosity, because viscous forces prevent water from moving. In order to move water inside the pores of a porous medium, you have to overcome viscous forces. You have to have a pressure gradient. Here, there is no pressure gradient. We bring water in contact with the bottom of this paper. Nobody is pushing water up. Temperature everywhere is the same. So why is the water going up? Now, let me show you the movie. But what we also have done, we have 2 cameras here. One is an infrared camera, and the other is a common CCD camera. The CCD camera shows you what happens in terms of the surface of the paper. The infrared camera measures the temperature. And look what happens. Now, this is the setup. And that's the 4 pieces of paper. And here, you see that at the bottom, this dry paper is white. And then it darkens from the bottom as the water moves in. But what you also see on the right-hand side, the infrared camera, you see that there is a red area showing higher temperature developing wherever the front of the water imbibed into paper is. Why is the temperature going up? Because, as I told you, everywhere temperature is the same. So and this rise of temperature I show you is 1 degree. It's not small, and you're talking about a very thin piece of paper. It's only 100 micron thick paper, and so this is amazing. The water goes up against gravity, against viscous forces, and also it produces heat. And the reason is because we are replacing within this paper we are replacing the air solid interface with water solid interface. The interfacial energy of air solid interface is larger than water solid interface. So when it is replaced, it releases energy. And that is the energy that is behind pulling the water up against viscosity and even creating heat. So I hope I have explained this to you, that we really, and we have done lots of different experiments with these different fluids, different kind of paper. We use hydrophobic paper, and you see that then that doesn't go up and there is no heat release. We can get a lot more heat release if you have a thicker paper, and so forth, so forth. It was a very nice experiment that I can explain during the short course. Okay, so one other thing that I'd like to explain is what is the difference between interfacial tension and surface tension. Often people use these 2 terms interchangeably as if they are the same. They are actually not the same. Surface tension is, so surface tension is the surface tension is the between a fluid, between a liquid, between a liquid and its own vapor. That is what is called surface tension. And if instead of its own vapor, so if you put the liquid in a container and vacuum, now that liquid will evaporate, and then the interfacial tension between the liquid and its own vapor is called surface tension. Now, if instead of vapor you have air, it's the same because the air or vapor will not be much different. So that is between liquid and air or its own vapor is called surface tension. Interfacial tension is between two liquids. So interfacial tension is between two liquids. So you really shouldn't mix these up. And here are some values of measured values of surface tension between air in contact with benzene and various liquids. It's a function of temperature, of course. You can see that here. If you increase the temperature, the surface tension goes down. Okay. We also have solids have surface tension, and those are the values shown here. And in fact, if you have the surface tension values of two different liquids, for example, liquid A and liquid B, then you can use Antonov's law to calculate the interfacial tension between these two liquids. So the surface tension of liquid A with air or its vapor and B with air and vapor, if you have them, then you can calculate. I'm not going to go into details of that. That's how it's done, but it can be done. And these are some common interfacial tension values, for example, between water and mercury, benzene and water and glass. We use these values to make some example calculations that we are not going to do here. So we go back to the question of what happens if you put a drop on a liquid. I usually ask this in the class, and they say, well, it depends on what, if you put a drop of liquid on a flat solid, what happens? And people say, well, it depends on what the fluid is and what the solid is. It's correct, but it's incomplete because it also depends on what is around that liquid. I didn't say it's air. They assumed it, but you can put this, for example, in oil and a solid and a droplet of water. So it depends on three things, three phases. Together, they determine what happens to a droplet, for example, or the interfaces between two liquids. And we are going to go through these shortly in one case, for example, here. So, for example, if you have a liquid like this, droplet of a liquid like this is the liquid. This window of GoToMeeting is always in front of my pen. So we have a liquid here, and here is the gas. Here is the interface, and here is the solid. Now, we said what happens to this liquid depends on these three phases. It actually depends on the interfacial energy or the interfacial tension of these three. And those are shown here. As you remember, interfacial tension is force per unit length. That is shown here. This is gamma liquid gas. This is gamma liquid solid. And this is gamma gas solid. So it depends on value of this. And these are acting, these three forces are acting on a contact line that is formed between the three phases. I show that here as a point because we are looking at the cross-section, a two-dimensional picture. In reality, this line goes all around, so it's a line really. But these three forces are exactly acting on the same line, every point exactly the same. So if sufficient to just look at this, this point, which is a cross section of the line, and look at the balance of forces. So what will happen here is that the balance of these forces. As you can see, the gamma ls is pulling to the right in this drawing, and the gamma lg is also pulling to the right, but then only one part of it, the component of it, is pulling to the right, and gamma gs is pulling to the left. And if you look at the balances of this in the horizontal direction, then you can write gamma gs is equal to gamma lg cosine theta. By the way, this is angle is theta. As you know, this is contact angle, and then plus gamma ls. And this is known as Young's equation, as you know. Oops. Let me move this. It's known as Young's equation. So this is actually simple. What is it telling you is that depending on this gamma ls and gamma L, if gamma gs is less than gamma ls, what does it mean? That means it's hydrophobic solid. Because if you remember, I said for hydrophilic solid, the interfacial energy between gas and solid is larger than the interfacial energy between liquid and solid, and so is the surface tension values. So what is shown here is really for a hydrophilic solid. Okay. Now there is another point I'd like you to pay attention. This is also shown almost everywhere in the literature incorrectly, and usually in the class I try to invite people to tell me what is wrong with this force diagram that's shown here, because it's really wrong. And if you look at force diagram, as I said, these are forces acting on this contact line. And we just agreed that if you have this balance here, the contact line is at equilibrium. But that's only in the horizontal direction. How about vertical direction? This contact line must be flying because there is only one force acting on it, and that is going up. This is gamma lg sine theta acting on the contact line. So the contact line must be moving into space. It doesn't. Why is that? What is missing here? There is another force missing here. Whenever you pull or push on a solid, you will have a reacting force that is equal to the force you are exerting. So actually, this interface that is pulling on the contact line causes the solid to pull back, and this is the force of the solid, and this is equal to gamma lg sine theta. And it's good to know that this actually is there, because if you look at the literature, here is one example, I think. Let's see. It's coming here. This is from a book. You see, they all show here is the middle, the three forces with no vertical force. And there is a very nice experiment I'm not going to talk to, but that people actually have measured the force that is pulling on the solid. And of course, if the solid is not glass, but some soft solid, it even deforms the solid because of that pull. So it's not good to know that. This interfacial tension also tells you what the order of wettability is. If you have, for example, solid grains, sand grains, as shown here, and then you have water and benzene and air. Now, if you look at the numbers that are shown here, you can see that the water-air interfacial tension is higher than the other two. This tells you that actually water and air don't want to be next to each other, because if they are, you have a large energy of the system. And we don't want, I hope you are hearing from me, because I got here a message that the internet is weak. I get a warning, I guess, if there are any issues. So you can see that the interfacial. Okay, perfect. So interfacial tension for water and air is larger than the other, which means that air and water hate each other, or hate each other. They don't like each other. So if you leave this to the system, the way it will rearrange itself, as you, I haven't shown here the interfacial tension for water and silice, but you will see that is the lowest. So that's why you will have actually water covering the sand, because the water-sand interfacial tension is low. And then next to the water will be benzene, because it has a benzene air is lower. So if you don't have benzene next to water, it should be air, but the air interfacial tension with water is very large. So it's much better if you have benzene, if you have benzene first, and then covering the water. So benzene covering the water, and then air in the middle. So that's the order of wettability. Next to the sand would be water, then water covering, benzene covering water layers, and then the air in the middle. And that's, again, because of this wettability. So I hope I have explained to you what are the basics, underlying forces that lead to capillarity. Now, with all of this, we should actually then be able to say what happens if you stick a capillary tube into a liquid. And there again, it depends on what the capillary tube is made of, what the two fluids that are involved are made of. That will determine what happens when you stick a capillary tube in there. In case of a hydrophilic glass, in the sense that if this is water and this is air or any other fluid, then the water will go up. But if it is a hydrophobic glass, or if the liquid is, for example, mercury, and here is air, then this is a mercurophilic glass, a glass that likes mercury, likes the air, aerophilic glass, and doesn't like mercury. And then when you stick it in the mercury, it will go down. Now, why all of this happens, one can explain this in detail, because actually if you start from the beginning, and if you have at the beginning a water surface, and then you stick a glass tube, you bring the glass tube here, bring it until it hits the water. Now you still have a flat water interface. So what happens from the point that the glass hits this water? And how is it that this water then goes up in the tube? How far does it go? All of this can be explained by the concepts that I just described to you, which, as I said, given the time, we'll have to do that some other time. Okay, but we can write the balance of forces for a piece of interface. This interface can have, in general, two curvatures, because you can have a curvature in this direction, and you can have a curvature, let me use another color. So you can have a curvature in this direction, and that is this radius R1, and you can have a curvature in this other direction, and that's the radius R2. And if you are going to write balance of forces, I'm sure you all know that you will get this formula, that if the pressure on this side is P1 and the pressure below is P2 of the two fluids that are on the two sides of this interface, then we can write that Pn minus P2 is equal to the gamma between these two times 1 over R1 plus 1 over R2. So this is actually the general Young-Laplace equation. And you can also write this as gamma 1, 2 times curvature in direction 1. Curvature is the inverse of radius of curvature. You can write it like this, or you can write it like 2 gamma 1, 2 a mean curvature, when the mean curvature is the sum of the two curvatures divided by 2. So this is the formula that I'm sure many of you know. Now, one of the questions students often ask me is, what is the definition of capillary pressure at the macro scale? Because they have seen this as a definition of capillary pressure is the difference between the pressures on the two sides of the interface. But as you just saw, we also have this as the definition of capillary pressure. Which one is it? Are they exactly the same? Well, actually, they're not. The first one is a balance of forces. This one is simply a definition. And they are equal only under equilibrium conditions. So I'm going to very quickly talk about that. You see, if you write the equation of force balances for an interface, it has this general form. I'm not going to go into details of it. As I said, this is going to be lengthy, where this gamma is the gamma is the mass per unit area of interface, time rate of change of velocity of the interface, and that is the acceleration. These are the surface forces within the interface. You can have surface tension. You can also have surface viscosity. These are the forces on the two sides of interface from the two fluids. So this is the fluid on, say, the non-wetting side. So if you have an interface, this is the non-wetting side, this is the wetting side. This is the surface tension in the wetting, viscous stresses within the non-wetting phase, pressure of the non-wetting phase, viscous stress of the wetting phase, and pressure of non-wetting. And you can even have a gravity for the interface. This is the general equation. And if we really simplify this and we write this in the normal to the interface, in direction normal perpendicular to the interface, we got this formula, which says the surface tension times the curvature of the interface is equal to the pressure difference between the two sides, but also the sorry. Wait. Also the difference in the viscous stresses of the two interfaces. Under equilibrium conditions, as you know, the viscous stresses are 0, and we get this formula. But under non-equilibrium condition, this is the forces. These are all the forces. And then you can see that we can call 2 gamma times kappa capillary pressure. And capillary pressure is not equal to Pn minus Pw under non-equilibrium condition, because you have this force of viscous forces acting on the interface from the two phases. And in order to show that, I'm going to show you a result of some simulations, but also some experiments. These simulations have been done by, let me remove this, have been done by Sheng and Zhu. What they have done is that they say, okay, let's have a tube. The tube has shown here at the bottom. And then we have an interface. There's a non-wetting phase. There's a wetting phase. And if this is moving to the left or can be moving to the right, then as you know, within a tube, you always have a parabolic velocity distribution. This is half of the interface. So the velocity distribution will be that velocity is 0. Let me take another color. Velocity is 0 at the wall, maximum in the middle, and then it goes down the other direction. This is half a parabola. This is the velocity distribution. Velocity is 0 at the wall, but not where the interface is, because this whole thing is moving, and the interface, when it meets the wall, cannot have 0 velocity. It must be a slip condition. And so when they zoom into this area, they see that actually the velocity distribution at the contact line is very complex. You have these circulations of the two liquids. And these are caused by those viscous stresses that I just mentioned to you. Okay? These viscous stresses, they cause circulations around the interface, and they have shown that they have calculated everything that, oh, Pn minus W is not equal to 2 gamma when there is movement. And in fact, to show that you really have these circulations near to interface, this is experiment we did. There is air flowing. These are solid walls, and here is a liquid. It was water actually, and you can see near this is the interface between air and water. See that the fluid is circulating, and this circulation exerts forces on the interface. Here is another one. We did it with different liquids. Sorry, a different velocity of the air. So the velocity is lower than here, and as the velocity of air is larger, see there is more circulation. So all of this, when in that work of Shen and Zhu that I mentioned, they calculated that these two are not equal, and in fact the difference is a function of the flow velocity. And if there is drainage occurring, then we have here a plus sign, and if the imbibition or the flow, the wetting phase displaces the non-wetting phase, we'll have a minus sign. And this is what I call non-equilibrium or dynamic effect in capillarity. So under equilibrium conditions, the capillary pressure is equal to Pn minus Pw, and that is capillary pressure. But if you have non-equilibrium, then they are not equal, and the difference depends on the flow velocity. So this was all at the micro scale. I don't know how much time I have. Well, actually, I'm close to my time, so I'm going to be rather quick. I hope I have explained to you what are the underlying concepts of capillarity. What is capillary pressure? How is that related to the molecular forces, wettability concept, and surface tension, and that it's not equal to Pn minus Pw at all times, only equilibrium. Non-equilibrium is, and exactly the same at the macro scale. Now, at the macro scale, you know, I'm sure all these kinds of curves, capillary pressure saturation curves, and they say at the macro scale that capillary pressure is Pn minus Pw. Now, at the macro scale, there is no mention of surface tension anymore, because that only happens within the pores, right? And but then this is simply assumed at the macro scale, and then it's said to be a function of saturation. All of the sudden, saturation comes in. We didn't have any saturation at the micro scale. So one question you can ask: can you really derive such a relationship? Let me pass through this. See, this is the equation at the micro scale, at an interface inside the pores. If you average this, now you have to average it not everywhere, but only over the interfaces. Whereas the equation of macro scale pressure, which was shown here, these are average pressures. They are average over a very large numbers of pores, 1,000 pores or so. And how is that linked to this macro scale? Sorry, to this micro scale formula that we know for capillary pressure. Now, you can never ever average this equation and get the macro scale capillary pressure relation that we know. In fact, if you are going to average a relation like this is the Young-Laplace equation. Now, we can write the area of the interface in this form related to the radius of tube and contact angle, and you can write that the PC is a function of the area of interface. So if anything, if you average this over thousands of pores, you will find that the macro scale capillary pressure, I showed with capital P, has to be a function of the interfacial area and not so much a function of saturation. Now, we have found actually that, and this is something that I'm not going to go through this here. We have developed a very rigorous approach to derive these macro scale capillarity formulas. And when we did that, we find that under equilibrium condition, you can indeed derive this equation, this equation that the Pn minus Pw is equal to Pc, and it's not necessarily just a function of saturation. But how about under non-equilibrium condition? I'm going to briefly talk about that. So we want to talk about macroscale capillarity, which means that average of pressures, average values under non-equilibrium conditions. And I'm going to show you a simple system. The simple system is that you have a tube, you have oil, and you have water. If there is no flow, then there is an oil pressure. This is P oil. There is a water pressure. This is lower, and the difference is the capillary pressure that is here. So if you plot along this pressure as a function of distance, you get these curves, flat, because there is no flow. If there is in the horizontal direction, the pressure in each phase is constant. Okay. Now, if there is flow, what happens? Because there is flow, there must be a gradient in pressure of oil, a gradient in pressure of water. At the interface, there is a jump equal to capillary pressure. So now if you average this, the average over the oil phase, average pressure will be somewhere here. This is the average oil pressure, capital P oil. And the average water pressure will be somewhere here, P water. Now you can see that the P oil minus P water is not equal to Pc. It's actually larger than Pc. This is under drainage conditions. And in fact, if you reverse the process, you will find that the difference between P oil minus P water is smaller than Pc under imbibition conditions. So we even calculated that, and we calculate that from the LDT, and we can find that under non-equilibrium condition, the average oil pressure minus average P pressure is not equal to Pc, and the difference relates to how fast the drainage or the imbibition occurs. So this is what we call non-equilibrium capillarity, and there is a coefficient involved, this tau, which is the coefficient of non-equilibrium capillary pressure. So we have done a huge amount of work to verify this equation. To not only we, many people have done that, to calculate and measure the tau and how it works for different liquids and so forth. I'm not going to go into that. I'm going to touch upon another point, and that is one thing we also know about these capillary pressure curves, that they are not they are hysteretic. That drainage curve is different from imbibition curve. These are the primary drainage curves. You can also have the main drainage and main imbibition curve. They are hysteretic. And actually, we started with saying that, oh, Pn minus Pw is a function of Sw. Now, this means a curve, an algebraic relationship. But now we know that it's not one relationship. There are many relationships possible, whether it's primary or main, or you can even have the scanning curves. So why is that? Now, you can go into details of what are the underlying hysteretic causes of hysteresis, but how should we, at the macro scale, beyond, okay, what is the underlying mechanism, at the macro scale, how should we describe this in terms of macroscopic quantities? And I'm going to show it to that. So one thing, these are curves that are measured by Morrow. And what you see here, this is for drainage curves. These are imbibition curves. As you can see, there are lots of scanning curves. To get what I actually want to say that we have here, we don't have a number of curves. We have a lot of equilibrium data points, because these are all equilibrium values. So it's not just those curves. Actually, you can fill up that whole space with equilibrium points between Pn minus Pw or capillary pressure and saturation. So if you show this to any mathematician, he will tell you, oh, it's not just the Pc a function of saturation or water content. You are missing a third variable, because this shows that there is not a unique relationship. There must be a third variable that, because you don't take that into account, you get these many data points. Now, if you take a third variable into account, that means you don't have curves, you have a surface. Because if PC is a function of not only saturation, but something else, and I'm going to say in a minute that something else, interfacial area between the wetting and non-wetting phase, then we have a surface. And the projection of that surface into this plane of PC will give you this projection domain to show that actually PC is not just a function of saturation, but also interfacial area. I'm going to show you this think experiment. We have done the real experiments too. Imagine there is water bucket and there is a blob of oil in there. And this has a given radius r, therefore it has a given volume. It also has a given interfacial area per unit volume. Now, if you shake this and break this one bubble into 8 bubbles, now the volume has remained the same, but the radius has become smaller. Now you have a larger capillary pressure, twice as much as you had here. It's the same saturation. So capillary pressure is not just a function of saturation. What is really changed here is the interfacial area that has changed. It's now 16 times what it was here. So it actually clearly shows you that capillary pressure is not just a function of saturation. And by shaking, that's what happens in a porous medium when you drainage, imbibition, you get all those equilibrium points I showed you in red. And that means that you're really changing the interfacial configuration between the two liquids. So this concept has been actually tested and studied by others. This is from work by Celia and one of his students, Mike Celia. What is shown here is capillary pressure that is here as a function of not only saturation, but also interfacial area. If you plot it only, these are from Poroscale network modeling. So they are all calculated from a model. If you plot only PC versus saturation, you get these typical curves that you all know, the hysteretic curves. But if you plot it as a 3-dimensional, then you get a surface, and that's a unique surface. Projection of that surface into this plane, as I said, will give you this whole domain, and every point in that domain is a possibility. These are experiments we did using a micro model. These are PC plotted versus saturation for many scanning curves. And if you plot it as a 3-dimensional surface, then the points all fall on a surface that is the same for drainage and imbibition. This is drainage points plotted. This is imbibition points. And the difference between these two surfaces is less than 10%. We can even fit a formula to that, showing that PC is not just a function of saturation, but interfacial area. So the general non-equilibrium capillarity theory is that the pressure difference between two fluids in a porous medium, this is macroscale, is equal to capillary pressure under static conditions, and the capillary pressure is the function of saturation and interfacial area and not just saturation, and under non-equilibrium condition, they are not even equal, and the difference is a non-equilibrium term, depends on how fast you do the drainage or saturation. That the fact that these are really important, and it's not just a matter of theory, they explain phenomena that we cannot explain otherwise mathematically if we don't have this term, is this experiment that has been done by Hassanizadeh. See, this is a sand box, and they put water on top. And you expect if you put water on top, it goes down as a front. It doesn't. It forms these fingers. So this, if you model this using a standard unsaturated flow theory, you never ever get fingers. You put water here, equilibrium, equal height everywhere. This is homogeneous sand. This will go down as a front, not as fingers. And fingers will develop if you include this term in your model. Then you get unstable domains. And now that's shown here. And as I see that the time is over, so I'm going to actually stop here. Let's see. Yeah, so these are simulations using that extra non-equilibrium term. As you can see, they put water here and fingers are developed. And what is more, at the tip of the fingers, saturation is higher than behind it. And these are obtained by this numerical modeling using a non-equilibrium capillarity theory. Okay, well, thank you for your attention. I hope you have found this useful. I'll be happy to answer questions you may have. But maybe Dr. Karimai will say something else first.
Yes, thank you very much, Professor, for the nice and very interesting presentation. I would like to take this opportunity and mention that PetroTeach will run this course by Professor Hassanizadeh in 2 slot times in 2021, as you can see, where Majid will talk about origin of properties such as wettability and capillarity, basic formulas for capillarity at the porous scale and also core scale. He will talk about laboratory measurement of capillary pressure saturation relationship, capillarity at the reservoir scale, and the link to laboratory measurements, and many other interesting topics. And remember that PetroTeach will offer 20% discount for PhD students group and also early bird registration. So also before starting Q&A, let me remind you all that we will have a webinar tomorrow by Professor Haidari on fundamentals of carbonate reservoirs. And also next week, the role of geomodeling in the multidisciplinary team will be given by David Garner on 9th of December. So let's start the Q&A session. The first question is regarding the interfacial tension and its modeling. The audience asked that, did you try to compare the experimental results to molecular simulations like Monte Carlo type of droplets, for example?
Yeah, no, I have not done any molecular dynamics simulations. The smallest scale I have done simulations are really the, say, continuum scale of pore within the pores, fluids within the pores. But I know others have done that, and they have had success at various degrees. The thing is that with molecular dynamics, often you cannot model more than a couple of thousand molecules, whereas the surface tension measurements are really involving millions of molecules. So I'll not be surprised if there is not a good, always good comparison. But under certain conditions, people have obtained, but I haven't done that, no.
Okay, the next question is if water does not move as in its interstitial state in the reservoir and only oil is flowing, could we say capillary pressure is equal to 0 in this case?
Well, depends on which capillary pressure you're talking about. For capillary pressure to exist, you don't need movement of phases. Even if the phases are not moving, you still have capillarity in the sense that the interface between, look, oil and phase are two immiscible liquids. If they are immiscible, if they are miscible for any reason, you have lots of, for example, you have lots of surfactants for any reason, then we don't have that much capillarity. But if they are immiscible, there must be capillarity, and that is determined by the curvature of the interfaces between them, as I said, and has nothing to do with the movement, if I understand the question correctly.
Yes, the next question is asking, can we say that density has came from these forces that molecules make?
Yeah, of course. Well, density has nothing to do with forces. Density is the mass per unit area. So if you take a volume containing the molecules, then density is the mass of those molecules per unit volume. This is the simple definition. There are, of course, other definitions of density where you can involve a sort of a volumetric density function, so that you don't need to define a specific volume or a finite volume. But no, it's not really, density is not related to forces. It's more, at least not in Newtonian mechanics. It's mass per area.
Okay, another question asks, what happened in fractures that there is no capillary pressure? Why we don't have any capillary pressure in fractured reservoir?
Not sure what once again, which capillary pressure. There are people who talk about macroscale capillarity or microscale capillarity. There are people who say that in oil reservoirs, especially say fractured reservoir, then the macroscale capillary pressure is negligible. That could be compared to other forces that, and in fact, there was no time to go through this. If we do the kind of averaging I just explained to you for a single tube and do this for a much larger domain, for example, at the reservoir scale, you can see that the pressure gradient you have in phases will be such that the pressure difference between the two phases could be much larger than capillary pressure, because the capillary pressure really is the one that you have at the meniscus, and that is never zero. It just could be negligible compared to the pressure difference between the two phases when there are large viscous forces in active. And yeah, there was no time for me to go through that, but I can show that.
Yes. One more question that we got. Thanks a lot, Professor Hassanizadeh, for the nice presentation. Just I have one question: how we can improve commercial numerical simulations for your developed capillary derivations in microscale?
Microscale or macroscale? Because at the microscale, for example, you have open foam. There are various lattice-Boltzmann models. They are fine as they are. We don't need to change anything there because they basically solve Navier-Stokes equation. There are always issues involved at the interfaces, but I would say the commercial simulators are usually for macroscale, right? Macro, not micro. Do I understand that correctly? Hassan is macro.
Yes, he's written micro, M-I-C.
Yeah, but I would say that's macro simulators that we have. And for those, indeed, you could consider including this non-equilibrium term that I mentioned. It's been done by some. For example, Dumux is not really commercial, but it's a very large simulation package developed at the University of Stuttgart. They have included non-equilibrium term. But including the non-equilibrium term is not a major effort, but people have to see the value of it.
Yes, and also one more question. Can we say capillary pressure will depend on contact line instead of interface area?
Well, I wouldn't say instead of. It could be also depending on the length of the contact line. But look, I didn't have time to go through this. I am not throwing interfacial area into the equations just to have an extra parameter or a variable. The reason that is there, I explained it through some, say, considerations that I shared with you. But the reason is that if you start with a very rigorous thermodynamic development of macroscale theories, then automatically interfacial area comes into the picture. Contact line length may also come, but that would be actually a lower degree improvement of the theory compared to the interfacial area. Think of the thought experiment with one big bubble breaking into 8 bubbles. Think of that. And that was not in contact with the surface. If it is in contact with the surface, then it is, of course, the contact line can come in. But I'm sure, and I can share the information with the interested audience at some other point, maybe through email, where the derivation leads to this interfacial area coming into the theory.
Yes, thanks, Majid. We have limited time. Just as a last question, when the question is that when trapped into porous space, oil ganglia shows often a high curvature distribution. So it is not at equipressure. Why are they immobile? Why are they immobile?
Yeah, why they are immobile could be many reasons for a specific condition. But if I understand the question, says that the curvature is higher. Is that what you said? Larger curvature?
High curvature, often a high curvature.
Yeah.
Oil ganglia shows high curvature.
And I wonder, when you say a high curvature, that means capillary pressure is larger. That can happen indeed when you have you are pushing and you are increasing the pressure gradients. Then that will cause the curvatures. But usually it's not on all sides. It's on the flow side that you will have a lower curvature. On the opposite to the flow side, you will have higher curvature. That's at least what I have noticed, both in experiments and simulations.
Okay, thank you very much, Professor, and also thank you very much, everyone. Before finishing the webinar, I would like to mention that you will receive an email from PetroTeach contains a link for the video and PowerPoint presentation of the today webinar in YouTube and also SlideShare. The email is also contains more information about the online course, which will be given by Professor Hassanizadeh. So thanks everybody, and hope you enjoyed this webinar, and hope to see you in other webinars of the PetroTeach. Thank you. Bye-bye.
Everyone. Bye-bye.
Bye-bye.